Have you ever wondered why learning vectors seems to be one of the most challenging topics in all of A-level mathematics? While it appears that there are many formulae that one needs to memorize, we can actually develop these ideas one step at a time, starting with lines. We are all familiar with the line with equation y equals to mx plus c. What this tells us is that we start from a fixed point C and travel in the direction m. This idea can be extended for lines in three-dimensional space. We start from a fixed position vector A and travel however many units we want in the direction D. We can even go the negative direction. This gives us the crucial equation of the line r equals to a plus lambda d. And this describes a line that passes through the point A with position vector A and direction parallel to D. Sometimes we are interested in the actual coordinates of the points that lie on the line. For that purpose, we'll expand each of the vectors, we can combine the right hand side using some vector addition, and we can compare the coordinates to equate them with one another. Assuming that d1, d2 and d3 are non-zero, we can isolate lambda and equate them with one another to obtain the Cartesian equation of a line. But what happens when we have two lines? Do they always intersect one another? For example, we have these two lines given by slightly different position and direction vectors. To find their points of intersection, equate the two expressions together. Doing a bit of vector algebra, we can obtain that lambda and mu are both equal to 1. Since we can obtain solutions to this vector equation, we can conclude that the lines must intersect. But what about this other line with a slightly different position and direction vector? Solving the vector equation again now gives us lambda being equal to t and mu being equal to 1 plus t. This means that we actually obtain an infinite number of solutions for lambda and mu. And that tells us that these two lines have infinitely many intersections. But if two lines have infinitely many intersections, they must be identical lines. But perhaps the position vector of the second line might change. This will actually cause us to have no solutions for lambda and mu. Nevertheless, we can still say that the two lines are parallel, and the reason for that is that the direction vectors are parallel. In this case, they are actually identical to one another. But consider yet again another line with a different position vector and direction vector. This time we will not get any solutions for lambda and mu. As such, we call these lines skew because they don't intersect and they aren't parallel to one another. We can use this idea to investigate the ratio theorem. Given vectors a and b and a point that lies in between the tips. This point divides the line segment into a ratio of lambda to mu. A natural question to ask is, how can we find the position of this particular point? We'll represent it using the vector r. Since vector addition can be thought of as reaching a final destination, we can first travel along the vector a followed by a shrinking of the white vector in order to reach the point. The shrinking will happen proportionately, and therefore we have the factor lambda over lambda plus mu. Doing a bit of vector algebra, we will obtain the ratio theorem, which tells us the location of a point that lies in between the tips of A and B. A really important special case is when the ratio of lambda to mu is 1 to 1. This helps us obtain the midpoint of the tips of vectors A and B and is known as the midpoint theorem. Another way to think about the vectors A and B is by considering their angle. Using A and B, how can we obtain the value of the angle between them? This should bring back memories from high school trigonometry, because if we were to connect the tips once again, we'll obtain the vector b minus a, and we know how sides of a triangle relate to an angle. We can use the cosine rule. Furthermore, to calculate the length of the vector, we'll employ the three-dimensional version of Pythagoras' theorem. Substituting all of the different calculations and simplifying, we will obtain a sum product being equal to mod A mod B cosine of theta. This sum product on the left side is a really useful quantity which we call the dot product. And just this algebraic definition of the dot product yields many algebraic properties. For example, we can swap the positions of the vectors when it comes to dot products, and the proof is rather straightforward. We can expand out the left hand side using the vanilla dot product. We can swap the A's with the B's, but this is simply the expression for the dot product of B with A. In a similar manner, we can prove many algebraic dot product properties, which will be useful for manipulation purposes. However, the more insightful approach to the dot product is the geometry. We can summarize the left-hand side with A dot B, and this tells us that the dot product captures the angle between the two vectors. This yields several really interesting properties. For example, the dot product of a vector with itself is going to be mod A cos 0, but cos of 0 is simply just 1. Another really useful property is when the two vectors A and B are perpendicular to each other. The angle between them is 90 degrees, which means that the cosine of the angle, being cosine of 90 degrees, must be 0. But that means when multiplying by the modulus of A and the modulus of B, we will get 0, but this is simply the dot product being equal to 0. How then do we find the angle between two vectors once again? If you know the vector A and you know the vector B, you can obtain the angle theta between them. In fact, taking modulus on both sides, we can have a very succinct formula to find the acute angle between two vectors. In particular, if we have two lines with direction vectors d1 and d2 respectively, we have a very straightforward formula to help calculate the angle between these two lines in terms of the angle between these two direction vectors. Finding the angle between any two geometric objects can be reduced to finding the angle between two useful vectors. Another useful question would be, how can we find the length of projection of the vector BA onto the green line? Rather than having to memorize many formulae, we can use basic trigonometry to see that cosine of theta is L over the modulus of BA. However, we already have a formula for cosine of theta. That is simply the dot product formula. So we can set the left-hand side to equal the right-hand side, and what this tells us is that if we know BA and we know the direction vector D, we can instantly obtain the length L. Now if we do a little bit of algebra, we will actually obtain the formula for the length of projection. Once we have the length of projection, we might want to ask how to find the perpendicular distance. And since we have a right angle triangle, we just need Pythagoras' theorem. If we know the vector BA and we have obtained the length of projection L, we can very easily find the perpendicular distance D. However, we might be a little bit more stringent in our discovery. We don't just want the distance from A to the line, we want the coordinates of the point when it intersects. We call this the foot of perpendicular. Since the foot of perpendicular lies on the line, it will have the form B plus lambda D. But since F is the foot of perpendicular, the vector AF must be perpendicular to D. But if two vectors are perpendicular, their dot products must be 0. We can write AF in terms of the position vectors and substitute the expression for OF. Do a little bit more algebra to obtain lambda. We can back substitute to obtain OF. But we could ask the question, what happens if we take A and reflect it about the line? The key observation is that the foot of perpendicular is the midpoint of A and A prime. And if we know OA and we can calculate OF, we can easily obtain OA prime. What if we take an entire line and reflect it about the green line? Then the reflected line is a line and therefore it has position vector B and direction vector BA prime. And we know how to calculate each of these vectors using previous ideas. And using these ideas, we can solve problems involving light rays. We'd like to extend this idea to two-dimensional objects, known as planes. Just like the situation of the line, we'll start with a fixed point A, will travel lambda units in the direction U and mu units in the direction V. This gives us a plane which might be a little bit difficult to work with. But what's interesting is that no matter which two vectors you have on the plane, they always have a normal vector that is perpendicular to both of them. This motivates us to define a different kind of vector multiplication from dot products called cross products. The cross product of two vectors is comprised of cross terms. And just like dot products, cross products has many useful algebraic properties for manipulation. The last identity in particular tells us something interesting. It tells us that the result of U cross V is a vector that's perpendicular to both U and V. This means when we take the respective dot products, we will get 0. Now, considering the vector equation of the plane, we can apply the dot product with n on both sides, do a bit of dot product algebra, And since u.n and v.n are 0, we obtain the scalar product equation of a plane, which is determined by its position vector a and the normal vector n. Just like with lines, we can write the vectors in terms of the coordinates to obtain a Cartesian equation of a plane. Now that we have a plane in terms of a position and a normal vector, we can ask many interesting geometric questions. For example, how can we find the angle between a line and a plane? While at first glance it may not be obvious, the key trick is to take advantage of the normal vector of the plane. The line makes the complement angle alpha with the normal vector. This tells us that alpha is the angle between the direction vector of the line and the normal vector of the plane. But once we have the angle between two vectors, all that we need to do is employ the dot product. And we can expand alpha to mean 90 degrees minus theta. Once we know what d is, and once we know what n is, we can easily obtain theta. Another interesting question is to ask how can we find the perpendicular distance from a point B to the plane. Calling the distance d, we can connect a and b via a vector, and we observe that the cosine of alpha is d over the modulus of ab. On the other hand, we can include the normal vector of the plane and see that cosine of alpha is actually determined by the dot product of AB with n. And once again, if we know what AB is and we know what n is, we can do some simple calculations to get d. Doing a bit of algebra, we get this succinct formula for the perpendicular distance from B to the plane. And just like before, we might be interested in the length of projection of AB onto the plane. But since we have a right-angled triangle, we can simply apply Pythagoras' theorem. Once we know what AB is, and we know what D is, we can easily obtain L. And just like before, we might be interested. What is the foot of perpendicular from B to the plane? Since the plane has normal vector n, the point F must lie on the line with position vector B and direction vector n. But since F lies on the plane as well, it is the intersection of a line and a plane. We can now apply some dot product algebra to obtain lambda, and once we have lambda, we can easily obtain F. And once again, we might be interested in considering the reflection of a point in a plane. But the solving technique for this is not new for us. F is simply the midpoint of B and B prime. If we have OB and OF, we can easily obtain OB prime. But what if we're considering the interaction between two planes instead? Clearly the two planes intersect in a line. How do we find the equation of this line? Let's include the normal vectors of the two planes. And since the line lies on both planes, the direction vector D must be parallel to both planes. But that means the direction vector D must be perpendicular to both normal vectors n1 and n2. But what vector is perpendicular to both n1 and n2? That will be the cross product of n1 and n2. And since in principle we can choose any direction vector, let's just take the direction vector to equal the cross product. This is how we find the equation of the line of intersection of two planes with a common point A, and sometimes we might even condense the direction vector in terms of the normal vectors. Finally, we might be interested, how can we find the angle between two planes? With a little effort, the angle theta formed between the two planes is actually equal to the angle formed between the two normals. But once we know that theta is the angle between the two normals, we simply need to employ the dot product to obtain theta. So while vectors may seem rather daunting, it is buttressed by four crucial formulae: the equation of a line, the dot product, the cross product, and the equation of a plane. These four formulae sum up A-level vectors in a nutshell.